a quick recap of what we were doing in the last class. We were talking about the scattering matrix. And if we have an N port and if the characteristic impedance corresponding to the transmission lines attaching the N port to the outside world is all the same and equal to Z naught, then we can simply basically relate the amplitude of the complex magnitude of the incident wave at every port to the reflected wave at that port through a matrix. So, that is V1 minus V2 minus blah 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 Vn minus is the scattering matrix times the reflected waves are basically Vn plus, all right. And we saw that there is a need for these scattering parameters, right, and the need is motivated by practical realities. When you want to measure admittance parameters or impedance parameters of an N port, and most commonly a 2 port, one has to terminate the port with either an open circuit or a short circuit, and of course, in reality it means that you will not be able to place the short exactly at the boundary of the port. You will have to connect it through a cable. A cable is modeled as a transmission line, and if you terminate a transmission line with a short circuit, at the other end of the line you can see an impedance which can go anywhere from being a short circuit to an open circuit to anywhere in between. And consequently you basically end up with in a situation where if you are trying to measure an active device, right, for example a transistor and stuff like that, you are you will be in a situation where the whole setup, namely the transmission line, the transistor and the entire measurement setup starts to oscillate. That basically means that you will not be able to measure the parameters properly. And why? Because remember, a transistor is basically a nonlinear device, and whenever we talk about impedance or admittance parameters, what exactly do we mean? They are basically you linearize that transistor about the operating point and get a get a 2 port which is linear, and then we assume that the signals that we impress on this 2 port are sufficiently small to satisfy the small signal approximation, and then all the other theory makes sense. But if the whole setup is oscillating and once something starts to oscillate, it only limits when something somewhere in the setup saturates, then it is no longer small signal, and this notion of small signal parameters basically does not make any sense, right. That is the best case. The worst case, of course, is that the amplitude of oscillation becomes so large that the power dissipated in the transistor becomes either the power dissipated becomes large, or the voltage across the transistor, the current through the transistor becomes so large so as to breach its maximum permissible voltage and current values, and that will cause destruction of the transistor. And sometimes if the transistor is a large high power device, then it is entirely possible to have an accident. So, the way around it is to avoid, the root cause, as you can see, is that even though we terminate the cable or the transmission line with an open or a short circuit, at the other end it can look like something completely different, and the only way to get around this problem is, in other words, we need to terminate the transmission line in some magic impedance, and we want to be able to see when you look at the impedance on the other side of the transmission line, you want to make sure that, I mean, what you want is that the impedance should be independent of the length of the transmission line, right? And the only way to do it is if you have a transmission line with characteristic impedance Z0, then you basically terminate it also with Z0, and this way you can have a transmission line which is which can be in principle arbitrarily long, I mean then so therefore the real world difficulty of having to run a cable from the port to the termination basically, or to the measurement equipment for that matter, right, that problem goes away, and you are now able to measure. So terminating the cable with 50 ohms is equivalent to terminating the ports with 50 ohms at the location of the port, even though the actual port may be a mile away from your terminal. Does it make sense? Right? Very good. And we also know that V1 square by Z0 or mod V1 square by Z0 quantifies, therefore, is the power going in the forward direction or the incident power, and likewise on port 1, and likewise V1 square by Z0 is the power reflected from port 1, right? Yes.
What if our line impedance will not match to the impedance, the terminating impedance, both are not Z0?
Oh, of course, now he brings up an interesting point. He says, oh well, this is all great in theory, right, where the characteristic impedance of the line is exactly the same as the terminating impedance, right. So what happens, if, of course, in reality you will never be able to make the characteristic impedance of the line exactly the same as the terminating impedance, and what do you think will happen? Well, we can do the math, right, but what would you expect? It will become dependent, but what comment can we make about that dependence? I mean, you should expect that as you get closer, as the terminating impedance gets closer and closer to the characteristic impedance of the line, the reflection coefficient becomes closer and closer to 0, and therefore you basically end up with something which is, I mean, it does indeed change over over the length of the cable, right, and the impedance will no longer, at the other end of the line, will no longer be equal to Z0, right. There will be some frequency dependence, but that frequency dependence, that frequency dependence will be small compared to what you would have seen if you terminated with a short circuit, right. And but this is indeed a practical problem as far as measurement accuracy is concerned, right, and we will see what is done in practice to fix this problem, right. So the long and short of it is that if the terminating impedance is not exactly the same as that of the line, right, yes, that is, it is correct that the impedance will now be a function of the length of the line as well as the frequency, right. However, it will almost be equal to Z0, right, and the variation in impedance with respect to frequency or with the length of the line will be small, and compare that with when you terminate with a short circuit, you thought you had a short circuit, but you can actually see something which is open. All right. Okay. So now so let's consider this N port again. I'd like to kind of draw your attention to a property of the scattering matrix for a general N port. What comment can we make about the sum total of the incident power on this network? I mean, is this like so simple that you think it's below your dignity to answer it, or is it so difficult that you have no clue what's happening? Okay, very good. Okay, all right. So I'll think of it. I'll think your answer to be the former and move on, right? So V1 square plus blah blah blah, right. All right, which can be written if you write the incident vector. If you put all these v1 through vn as a vector, it's simply nothing but, let me call that I don't know, we call that v plus. All right. So, this is nothing but v1 plus vn plus is the column vector of all the amplitudes of the incident waves, and therefore, the incident power in terms of this column vector can be written as 1 by z naught times v plus conjugate times sorry, v plus, I am getting, now there is plus, there is star, there is transpose, right. Okay, this times v plus. Does it make sense? I mean, just, I mean, you know, I mean, I am sure all of you agree that you know, this looks a lot more intimidating than simply writing this, right. Okay. And that is the whole purpose of going to university, right, where you make something simple and make it look all the more complicated. Because if you go tell your friends its power in one port is v1 square and n port is v1 square plus v2 square plus v3 square all the way up to vn square, like I says, why do I need you to tell me that? Isn't that obvious, right? Whereas now if you write this complicated looking notation with star and transpose and, you know, plus, all of a sudden it starts to look very impressive, though there is nothing much to it, right. Okay. Now, so now let us you know, pretend to be sophisticated and write an expression for the reflected power. Is what now? Well, if the input power is 1 over z naught times v plus star transpose times the vector v plus, what will be the reflected power? Oh, well, it does not require a genius to figure that out. That is basically v minus star transpose times v minus. All right. And what do we know about v minus in terms of v plus? This is, oh well, this is nothing but s times v plus, and what is this guy? What is this guy actually? That is s times v plus again, that times star. So, that should give you its conjugate, which is basically, come on folks, I mean, AB whole conjugate is, now people are thinking whether it's B conjugate A conjugate or A conjugate B conjugate, come on folks. Okay, all right. So, this is S conjugate as S star times V V minus star, sorry, V plus star, correct, and this transpose. So, our reflected power is this times S times V plus, all right, okay, and this must be equal to, you can write this as, well, this will be V, I mean sorry, I forgot the 1 over z naught. So, this is 1 over Z naught times V plus star transpose times transpose of the product is nothing but, I have to flip the order when you expand it out. So, that is basically S star transpose times S times V plus. Does it make sense, people? So, therefore, the reflected power is 1 over Z naught V plus star transpose S star transpose times S times V plus, and the incident, this is the PR, the reflected power. PI, again for your reference, is simply 1 over Z naught times V plus star transpose times V plus, alright. So, if the network is lossless, then what comment can you make? The reflected power must be the same as the incident power, right, okay, and therefore, this will happen if S star transpose times S equals the identity matrix, right. Identity matrix is of size n. And it turns out, I mean, do you know, if you have taken a course on linear algebra, you probably know this already, right. So, if you have a matrix and S star transpose times S is equal to I, what do you call that, such a matrix? Unitary matrix, right. So, S is unit, okay, if the network is lossless, right. In English, what does this mean? Yeah, which is equivalent to saying, you know, English now basically is now become right. It says all the rows are orthogonal to each other, which is sounds just as you know, Latin and Greeky to the uninitiated. So, which, yeah, that's correct, but what does it mean? If you take the ith row or ith column, complex conjugate it, multiply it with itself and add up all the terms that you get, you will get 1. If you do that with a column which is not your own, right, you will get 0, okay, that is all that there is to it. Okay, so, this is you know, something to bear in mind, and again, as you can see, you know, it sounds like something very deep, but as you can see, all that it means is that what is you know, how do you get this? What you push in is the same as what you get out, and in a less if you want to say this in a less pretentious way, you just basically say sum of V1 square through Vn square plus is the same as V1 square through Vn square minus. All right, that's that. Another quick point. If the N port is matched at all ports, what comment can you make about the S matrix? What comment can we make? When we say N port is matched at all ports, what does it mean? That basically means that whatever is incident on that port nothing gets reflected, and so what term in the S matrix quantifies what is reflected when you put something into the nth port? SKK, where K is the kth port, so SKK equal to 0. So basically, if the n port is matched to all ports, then diagonal will be B0. All right. And remember, we started off this entire discussion of this S parameters by saying, oh, we wanted to measure Y, but then we found that to be a practical difficulty. So we came up with this scheme of measuring, we came up with a new parameter set, that's the S parameter set. Now the question is, how is the S parameter set related to either the Y or the Z or any of these a bazillion other things, right? So let's just do, say for instance, how the S parameters are related to the Y parameters. So the Y matrix basically relates of an n port, basically relates currents to voltages, right, where I, Y and V are all I and V are column vectors with n terms, and Y is an n by n square matrix. Now the current is simply the sum of the current at the ports can be written as, we are trying to relate it to the S parameter set, correct, and the S parameter set only recognizes forward and backward going waves. So we need to express the current at the port in terms of the forward and backward going voltage waves, right. So what comment can you make about I? Remember, I is nothing but I plus or minus the total current at a point. Okay, how will you express this in terms of V plus and V minus? Okay, yeah, okay. So V plus minus V minus over by Z naught. So this is V plus minus V minus by Z naught, and that is Y times, what is the voltage? V plus V minus, correct, and therefore we are interested in finding, we take push all the V minus to one side and then V plus to the other side, and then just play with this. So V plus minus Z naught times Y times V plus equals Z naught times Y times V minus plus V minus, all right. So Z naught Y plus I times V minus equals I minus Z naught Y times V plus. Does that make sense? I hope I have not messed up. So V minus therefore equals I plus Z naught times Y inverse times I minus Z naught Y times V plus, and therefore what comment can we make? So how is the, given the Y matrix, how will you get the S matrix? Well, the S matrix is nothing but I plus Z naught times Y. Remember that Z naught is a scalar. This inverse times I minus Z naught. Right. Sanity check. What is the easiest number of ports to work with for the sanity check? one port, right? Okay. So, for a one port, S11 equals 1 plus Z naught times Y inverse, which is 1 plus Z naught times Y times 1 minus Z naught times Y, which is nothing but Z minus Z naught by Z plus Z naught, which makes sense, because this is Z minus Z naught by Z plus Z naught is nothing but the reflection coefficient, which also happens to be the the low, S11 of that one port. All right. Next thing, if the two port is reciprocal, let's say, for example, okay, so if the N port so if you have a reciprocal N port, what comment can you make about the Y matrix? Yes, people? It is the Y matrix is symmetric, which basically means that Y equals Y transpose, right. So, what does that mean as far as the S matrix is concerned? Remember, S is given by this guy. So, what is S transpose? S transpose is nothing but, what is S transpose? Or rather, if you replace Y with Y transpose here, what do you think you will get? Or rather, okay. So, basically, I will leave it as an exercise for you to prove that S, if Y is Y transpose, show that S equal to S transpose. So, that's so it turns out that if so in a two port, in a reciprocal two port, S12 must be equal to S2. Okay. And you can come up with similar ways of basically converting from Z to S and Z to S to any arbitrary set of parameters that you like. Okay, it doesn't make sense for me to go through all those parameter conversions.